All right, so what do we have here? We have the routine that implements the microkernel for the case where the microtile of C that's being updated is 4 by 4. And how do we proceed through this? Well, first we go and we declare and load a couple of vector registers, one per column of C. So hopefully you see what the convention is for naming these vector registers. Gamma 0, 1, 2, 3 underscore 0 stores the column indexed with 0, and therefore the entries 0, 0, 1, 0, 2, 0, and 3, 0 of matrix C. And to load that, you call this intrinsic function where you pass in the address of the first entry that needs to be stored in the vector register, and that automatically then also pulls in the next 3 entries that are contiguously stored with that entry that is indicated there. All right, so hopefully you see the pattern, and therefore you understand how these next statements load the columns of C indexed with 1, 2, and 3. Okay. Now we might as well go all the way to the end and recognize that these vector intrinsic calls then in the end store the result of having updated that microtile of C back into memory. All right, so what happens in between? Well, we said we were going to implement the microkernel by iterating over the columns of A and the rows of B, performing a rank 1 update with each column of A multiplying the corresponding row of B. And how do we do that? Well, we start by declaring a vector register in which we're going to load the PJ entry of B, but we're not just going to load it, we're also going to broadcast it. And notice that P is determined by this loop, and J is going to be explicitly instantiated to be 0, 1, 2, and 3. Notice that every time through we're going to use the same column of A, so we're going to load those entries into a vector register, which we have named 0, 1, 2, 3, P, to indicate that this is the pth column of matrix A. And again, we do a call to a vector intrinsic to do that load. Next, we're going to use the vector register that we had already declared to load and broadcast the P0 entry, the first entry in the pth row of B, after which we can update the column index with 0 of C by doing an element-wise multiply of what's in the first vector register, the one we named alpha 0, 1, 2, 3, P, and the current entry of B that we loaded and broadcast. And notice that at the moment that is the entry P0. All right, so this does essentially an AXP operation with vectors of length 4. Now, you need to do that for the columns indexed with 1, 2, and 3 of C as well, or the second, third, and fourth column of C. So to accomplish that, all we need to do is copy and paste these commands 3 more times, and then do some editing. Let's make sure we get back to where we needed to be. This is where we started to repeat. So notice that we next want to broadcast the P1 entry of B. So we just change that here. We want to say, oh, we're going to update the second column of C. Obviously, even if we got that wrong, it's just a comment, but let's make sure that we do this right. Then we want to update the column indexed with 1 of C, and bingo, we've done it. Then we want to load the P2 entry. We want to update the third column of C, and we do that. Oops, here we go. And then finally, we want to load the P3 entry of B, broadcast it, update the fourth column, And in theory, that will do. Okay, so let's see if we did this right. All we need to do is say make ji 4x4 kernel. And this compiles and links. And then it will execute this. Now, unfortunately, we're running this for pretty big problem sizes. You can see that right there. So this is going to take a little while. I'm going to just fast forward to the end. All right, so there we are. And notice that we're getting pretty good accuracy. As a matter of fact, this is the largest encountered. What that means is that we actually did our implementation correctly. And now let's have a look and see what the performance looks like. And on my laptop, we now see the performance indicated right here in green. And we notice we're starting to see quite a bit of an improvement in performance. Previously, on my laptop, the best we had seen was roughly around here, around maybe up to 15 gigaflops. And we're now getting close to 30 gigaflops, but only for very small problem sizes. So we're first going to now improve performance for small problem sizes, and then actually in week 3 we're going to see how to achieve better performance across the board.